Hello, everyone. In this video, we'll talk about sample spaces. So, what we're drifting into now is a way of using some of the basic statistics, but also journeying into a bit of a world of probability and understanding sort of risk and how we can quantify the notion of, you know, how often something might happen or what the likelihood of something happening is. Um, so if you're into sort of some of the games of chance, this will be a maybe fun uh, type of a series of lectures for you. So what we want to start with is we want to conceive of a set um, of all possible outcomes of a certain experiment. So we're going to run, and the experiment is really one that you can imagine. It doesn't have to be an experiment, but we'll call it an experiment. Um, so we're running an experiment, and the set of all possible outcomes ahead of time, thinking forward, is called the sample space. Okay, and it's denoted by the letter capital S. It looks a little bit like a 5, so let me rewrite it here. Okay. Now, what we'll do is we'll understand this set through examples. So let's start with the most common example, which would be flipping a coin. So your experiment is you're going to flip a coin. Okay. So what are the possible outcomes? Okay, so let's say it's a simple heads or tails situation. So you can either get heads, and we'll indicate that by the letter H, or tails, and we indicate that by the letter T. So our sample space is a set, and it consists of two possible outcomes: the case where you flip the coin and get heads, or the case where you flip the coin and get tails. That's it. So this is example one, but you can certainly make a more interesting example by flipping a coin, say, two or three or four times. So, let's adjust this. More interesting experiment would be to flip the coin twice, two times. Well, then we can talk about the first flip. It can be heads or tails. And then the second flip can also be heads or tails. But what we want to record are all possible outcomes of the entire experiment. So we'll think of the second flip after the first flip has occurred. So we'll say, okay, well, this is going to be heads or tails, or in the case where we headed tails first, this is going to be heads or tails. And so how can we sort of denote these possible outcomes? Well, we'll say, all right, there are four possible outcomes in this case, right? You can think of them as all of the possible ways that we landed here. We could get a heads and then a heads, which we'll write just as HH, sorry. We can get a heads and then a tails. We can get a tails and then a heads, or we can get two tails. And those are the possible outcomes in our sample space. Okay, what about three times? We'll just keep on going here. So this is a separate experiment, flip 3 times. Well, hopefully now you see, okay, I need 3 different letters. Kind of think of it as like making a word. You only got 2 letters in your alphabet, H and T, and you want to write down every possible word you can make, even if it's gibberish with H and T. So you have H, 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 you have H, H, T, you have H, T, H, you have H, T, T, then you have T, H, H, T, H, T. I'm going to give myself a little bit more room. Uh, we have T, T, H, and T, T, T. And we can ask about the size of this set in each case. And if we want to understand the size, we can see oftentimes what you'll do is you'll put bars around S to indicate the size, or you'll use the letter N. And in this case, we have size 2. Here we can see that S has size 4. Here we can see by counting that S has size 8. And you might guess, looking at these numbers, 2, 4, 8, that if we flipped n times, or let's say we flip, like n times, then the sample set will have 2 to the n possible outcomes. So the sample set gets bigger and bigger and bigger, exponentially large, in the case of flipping a coin. Each time we add an additional flip, it grows, it doubles. So that's a nice example of an experiment that you would run and where you might be interested in finding out the probability of different outcomes. And so we'll talk about that in the next lecture. But let's talk a little more about a few more examples. Maybe this is not the most interesting example. You can also do sort of rolling dice. So a pair of dice. And so you can, again, you can think of having sort of, one dice, it's a 6-sided dice. So you have a 6-sided dice, and then let's say you have a red one. And you want to roll both of them. Well, your first dice can be, anything 1, 2, 3, 4, 5, 6. You can get any of these numbers. Um, and but then for each of these numbers, you can get 6 possible numbers for your red dice. So we can just take, well, here, let's do this in the interest of making it efficient. We'll take this collection and we'll just duplicate it for each possible number that we can get for the red flip. So I've got 5, I need one more. And let's see, so we can get a 2. Oops. We can get a 1. We can get a 2. We can get a 3. We can get a 4. We can get a 5, a 6, and that's it. And in each of the possible black die situations, we can get exactly that type of a scenario for the red die. Sorry, this is going to overlap a little bit. And we'll end up with exactly 36 possible outcomes. So each of these pairs of numbers is a possible outcome, right? I mean, if we just point at one randomly, this would be the outcome of the black die is comes up as a 4, and the red die comes up as a 2. If we put this, they both come up as 5s. So this gives us our sample set in the case of rolling 2 die. And as you can see, there's a lot of different outcomes here. There's 36. 6 times 6 is 36 possible outcomes here. So even in very simple situations, the sample space can get quite large. So you could imagine another another example. Let's say the example of a football team, and maybe this isn't your experiment that you're running, but it's the experiment of watching a football team play for a season. So plays 12 games in the season, regular season, and the outcome is going to be sort of a question of wins and losses. So here you want to look at all possible outcomes. So, one outcome, if you're, hoping very much, would be that you have every single, I'm going to get rid of these commas actually, every single game is a win. So 12 wins. I'm going to see if there's three. Yeah, okay. So this would be one outcome where your team really did well and you're very excited. Sadly, this is maybe not the case for your team this year, but nonetheless, you can think, well, this is an outcome. Now, you can see already if you just flip one of these wins to a loss, you're already looking at a different outcome because, of course, this is an ordered set of wins. So switching this one to a loss tells us that, the fifth game they lost. So they were playing some, team from down south or something. And you can imagine, well, actually, there's an awful lot of, you know, possibilities here because, well, this is 12, you know, 12 games in the season. And so, what is how am I going to write down every single possibility? And the answer is you're not going to write down every single possibility. But you can imagine the sample space. So sample space is large. The sample space is very much like that of the coin flipping or coin flipping. So in a sense, this is a very similar scenario as a coin flipping. Instead of a H or a T, heads or a tails, an outcome is going to be a W or an L. And in this case, the sample space S has exactly 2 to the 12th outcomes, and 2 to the 12th is 4,096 possible outcomes. So several different possible things that can happen for your team's season, but and you don't want to, I'm not going to write those down. But this gives you an appreciation of sort of the complexity of trying to um, write down every single possible outcome. Nonetheless, even though it's a big number, it's a number that you can work with and compute, even in very, very complicated cases. Okay, next video, we'll talk a little bit about what an event is and how we can ask some questions in plain English about our outcomes and translate this into mathematics and subsets of our sample space.